Okay, welcome everyone to class 7, delayed owing to my being ill last week, of DCT 302. So I guess after a week of my being away, and I'm sure you can still hear it in my voice that I'm not 100% better, but after a week we can reflect a little bit on where we are. There are a couple of questions and issues either in the forums or things that have been brought up um, as chat or feedback items during classes that I'd like to address today. One of those things concerns wide gamut, so we'll have a talk about that. Basically, what happens if you put sRGB material into a wide gamut display or put wide gamut material into an sRGB display, and generally what's the advantage of wide gamut display capability working in either a D-Cinema color situation or an HD color situation. So we'll talk about wide gamut. That's item number one. And I guess this has been left over from several previous classes that we've got some open wide scale gamma discussion to have. And so I think I'll just kind of improvise on that. And I think those discussions, the wide gamma discussion and the general purpose gamma and gamut shift and QuickTime gamma discussion might occupy half of our time today. And then I'd like to go to perhaps a little bit of a free-flowing discussion about grading adjustments and grading controls. So, we all know that gamma is a common grading control. So we could talk about that and relate that to the gamma discussion. But also there's another set of controls in addition to lift, gamma, and gain, which are commonly used in color grading. Some grading systems use shadows, midtones, and highlights. And I thought it might be useful to discuss the similarities and differences between those issues, or between those ways of addressing image control. And then I think we'll have some time left today to do what I call constant luminance, or the constant luminance principle. And that's also all wrapped up in gamma in a very interesting way. So there's the outline, what I think I'll try to achieve for today's class. And so with that, let's get started on the wide gamut issue. And that wide gamut business, I think I'll just do by sketching. And if necessary, we can come back and do a review of some of the graphs and slides that I showed earlier. But for now, let's try to do it just by sketching. Okay, so let's start here. Let's start with the classic CIE XY diagram. Okay, so runs something like this, where this is the little x coordinate, this is the little y coordinate. It's called the chromaticity diagram. All of the colors lie within the horseshoe, and the horseshoe is joined up at the bottom end by the line of purples, which runs from basically pure red to pure blue. And as you've heard in previous classes, an imaging system, or let's say a display, can produce all of the colors that lie within the triangle formed by the primaries. So in this example, I'm picking primaries that are fairly far out, close to the spectral locus, which is to say they're very chromatic or colorful. I don't really like to use the word saturation. You could say color saturation if you wanted, but saturation is also what happens when your camera clips. It's an ambiguous term, and so I prefer colorfulness. Here I've chosen a red primary for my sketch that's right out on the spectral locus line, and that is characteristic of red for D-Cinema. However, you might remember that that 709 or sRGB colors don't go quite out to the spectral locus. They end up a little bit shy. So there's colors here in the yellows and oranges that can be produced by digital cinema, and digital cinema produces quite a colorful red. But these colors are not available by 709, which here is the inside triangle. 709 and DCI P3, which I'll go back here and label in black, they share the same blue primary, and blue is pretty close to the spectral locus. Of course, green differs dramatically. Now, if you have a wide gamut display, and so let's call P3 wide gamut. It's not as wide as you could have, but it's pretty wide. It's sufficient for all of cinema, of course. If you've got image data coming in 709 space, and you just present that to a wide gamut display, let's take our example of a P3 display, what happens is you basically move the color. Green is supposed to be displayed with these little x, little y chromaticities. That would be colorimetrically correct for 709 green, but if you just plug those numbers into a wide gamut display, you get green, which is wrong. It's too colorful. And the chances are that if you've got a nice skin tone in 709 coming in with your 709 image data, that if you just present that data to a wide gamut display, that skin tone will be warped to a different color, might not look like skin anymore, if you present that without treatment on a wide gamut display. Now, all of the wide gamut displays on the market have got signal processing internally that in the linear light space will apply a matrix that's selectable in the user interface of the display. So for all of the digital cinema displays, and I'm including here really high-end displays like the Sony E250 OLED, the Dolby display, mid-range displays such as the Azo or the HP Dreamcolor, all of those displays allow you to access a user interface to change the matrix. But when you do so, all you're doing is you're building the correct colorimetric transform into the data path to take the 709 numbers. You know, so if you take any of those displays and you set the user interface to 709 color space, what you're doing is inserting matrix that takes 709 colors and produces the correct RGB device values for the display device to produce colors that are correct for 709. So when you set 709 in any of those displays, you then no longer have access to the wide gamut colors. So you should think of this as being kind of a 709 compatibility mode to bring that display into a moderate color gamut of 709, and then making the wide gamut capability not any longer accessible. Now let's switch gears and think about the other way around. If you take one of these displays and you set it to wide gamut position, so let's say you set it to P3 position, then you're basically instructing the display that you're expecting P3 data to be presented to the display. Now, these displays are typically not exactly P3 native, although they're pretty close, typically. Any RGB LED illuminated display, which all of these are, is got native primaries pretty close to P3. Obviously, we hope they're a little tiny bit wider, because we'd like to make sure that P3 data gets displayed absolutely correctly. So typically the native primaries will be a little tiny bit wider than P3 even. And when you set up P3 in the user interface, there will be a matrix in the signal processing, but it'll make a little tiny adjustment, bringing the display capability into exactly textbook P3. Now, there's a few displays, and I'm thinking of, prior to Sony making the E250, they did an LCD called a BVM, although some people would argue it wasn't quite up to Broadcast Studio standards. It was called the L230, and there was a variant called the L231. And they didn't quite hit P3 blue. They fell a little bit short. But today's displays, all as far as I remember, do P3 completely. So when you dial up P3, they'll have a little matrix. But now, if you present 709 material, you've got this problem that they warp the material. So you've got to maintain control over what's the color space of the data coming in and what colors do you really want to be displayed. And so you can be in a wide gamut world, or you can be in a 709 world. And both of those things work fine. But now at class 7, I think you guys understand that you have to decide for a particular production what color space you want to work in. And so there's this notion in the grading systems and in the effects pipeline of what's the working space? In what color space is the mathematics done? And for an HD production, that would be sensibly chosen as 709. For a cinema production, it would be sensibly chosen as P3. And then you've got to decide, because typical productions involve some back and forth, where's the back and where's the forth? So where are the places in the workflow where you have to do these transformations from one color space to another? And is that particular color space transformation colorimetric, meaning the little x, little y values are preserved? In other words, the colors are preserved. And if so, is there clipping or is there gamut mapping? You've got to decide. So if you're in the usual situation where you're doing kind of high-end production, perhaps in P3 space for cinema, at what point do you go down to 709 space, say for an HD release? And you've also got this challenge of what do you do if you've got a large number of VFX artists and craftspeople who do not have P3 displays on their desks. Maybe they've got sRGB displays on their desks. Well, they will not be able to see all of the colors in P3. So the challenge is, if they've got 709 on their desks, what do you do? And so sometimes you'll do a colorimetric mapping, but that will involve clipping these wider gamut regions out and not letting them see that. And of course, it's a problem when the VFX artists can't see the colors in the data. The other option is just shrink and stretch. So just, you've got P3 data, but just present that to the display so that you can see all of the colors, even though the colors aren't accurate. And that's another option. And it's a challenge. All of this stuff is still a challenge, but I guess the desirable situation would be that you equip all of your VFX artists with at least ASO or HP class displays. And there's a few others. Maybe we could put Flanders in here. This would be more familiar, or also known as FSI, Flanders Scientific. This is more of a sort of video-ish display as opposed to a computer graphics display, but technically it's comparable to the ASO. The HP is maybe one little notch or half a notch lower in capability and in performance. But that it depends upon what arena you're working in, whether you're just working in VFX or whether you're also working in color grading and finishing and video. Okay, so that's a story about Gamut, of course. And so with that, if you've got any questions or comments on the chat line or just pipe up in audio, please feel free. But that's that bit of the discussion. Oh, and I guess just one passing note here, you've typically got in a pipeline where you're using ICC class color management. Now, I must say that's a little bit dangerous in VFX because you run the risk of color transforms either being imposed where you don't know about it, or color transforms being imposed where you didn't necessarily have control over how that transform was made. So it's slightly dangerous. But just speaking of color management in the ICC flavor, in tools like Photoshop, you've commonly got this dialogue that comes up when you're importing some imagery. Do you want this to be color managed or not? And your choices are basically, yeah, color manage it. Here's the name of a profile that will be suitable to bring that into the working space. And as I said, you get to choose whether your working space is, well, your working space can be any of a large number of potential choices, but the working spaces that we're interested in, I guess, would be P3 for digital cinema, 709 or sRGB, which for our purposes are virtually identical. Or in principle, as we go into the future, you will be given the choice of working space of ACES. Now, basically today, nobody using ACES is using ICC color management because ICC color management is really optimized for graphic arts and is just in the stage of being introduced into HD and cinema workflows. And I must say, After Effects is quite far along doing this. That After Effects probably leads in the use of ICC profiles for professional VFX and digital cinema and HD. But most of the people using ACES are not using ICC color management, and whether they will or not, we're not sure. So you get to choose your working space, and then when material is being imported into a pipeline, and you can use Photoshop as one example, you get this dialog box that says, import my material using a particular profile. So I'm trying to suggest this profile is kind of a pop-up box, which you can choose, and that will cause an ICC transform to be imposed on the way into the working space, which will be one of these. The other option you're given is something that might be called don't color manage, which is to say just use the RGB numbers. And this might be called preserve the numbers. And what this means, and again, I'm dealing with tools like Photoshop, not necessarily specialized VFX or CGI tools. But what preserve the numbers means is I just want you to import those numbers directly into the tool without applying any transform. What that means is the numbers are already in the working space. And so you'll need to be on the lookout for that. Now, I see several of you, or a few of you, are asking questions. So let me take this moment to pause and answer a question or two. So let's see. Jefferson is asking, how, and I guess you can all see it, how does the ACES system handle the conversion from the reference display to the selected ODT by default, clipping or compression? And so I guess the question is, and let me take a snapshot of my drawing here, and I want to capture some of those ideas for future use. But let me start anew and address Jefferson's question. So the in the ACES system, as you'll all remember, we've got the basic notion that ACES, and we can call it RGB, although you have to remember that both the green primary and the blue primary are non-physical. They're outside the spectrum. So we've basically got the ACES space as a working space, and we do our manipulation of image information in the look modification transform. And this will be controlled by knobs. So in effect, the grading in ACES is done in LMT. The look management transform in ACES space. So then we've got the IDT, which is coming in from whatever the camera or image source was, and it's doing the transform into ACES space. And once the look is modified, then we apply the reference rendering transform, which basically brings that ACES RGB space into a visual form suitable for 48-nit display. So let's draw a display. And at the risk of being a little dangerous, let's make that a display that's a direct view display. I put knobs on it, but I don't really want any knobs. I want that image data to just be displayed directly, but at around 48 nits. So dark like the cinema. It could be a projector if you want. Now that display has to have an ODT to transform the ACES space into the native space of the display. And Jefferson's question is about how do we handle the conversion? And keep in mind, there's going to be a few other ODTs potentially. I guess in the short term, you want to minimize the number of ODTs, so you really should, if you can, use an ODT that's suitable for your primary distribution, likely to be P3. So that ODT has got a special name, as you heard before. That's the reference display transform. So the RRT is fixed. I mean, at the moment, let's say we're in the beta stage of RRT, but it's the Academy's intention to fix that as RRT 1.0, and it remains fixed. There will be a reference display transform for P3 provided by the Academy. Whether they make that kind of a standard or whether they make that kind of a reference implementation, I'm not sure. So now with that context, Jefferson is asking, how do we handle the conversion from the reference display, well, we're not really converting from the reference display. And I hope I'm understanding your question correctly, but once image data has been transferred through the RRT, this is now OSI's space. It's the output color encoding specification, and it's transformed through the ODT to the reference display. That might be a Dolby display. So let's use that as our example. Or it might be, let's use as our second example, we'll put some people in the audience here and we'll make them view a big screen. This would be the P3 Cinema case. So there's an ODT for cinema. Now there is some tone scale compression that takes place in, let's make this the RDT for cinema. There is some tone scale compression that takes place in that transform. And, you know, if you've got a Dolby display, you might well use a Dolby ODT that doesn't have that compression. But you run the risk here that when you're mastering material, if you master looking at a Dolby display, you run the risk that the image is going to look somewhat different than it would look in the cinema to your end users. So, you know, you might want to master using an ODT where the Dolby display looks more like the cinema display and doesn't exhibit a contrast ratio of 10,000 to 1. I mean, the typical situation here, Dolby are claiming, and there's no doubt that this is true, that they're able to produce a contrast ratio of 20,000 to 1, where in the cinema, the DCI specs require exhibition at just 1,000 to 1. Now, the DCI specs say, well, we'd really like you to be mastering at 2,000 to 1, but we guarantee that you'll be able to exhibit at 1,000 to 1. But mastering at 20,000 to 1, well, this might not be a good idea. Now, you might want to master in a sense that's future-proofed so that you can accommodate a world where we evolve toward an improved viewing situation in the cinemas, you know, maybe 20,000 to 1 in the cinema. But this is not likely to happen anytime soon. And so I think in ACES, you're going to have to give some thought to how you master and which ODT we use. So now one or two of you are asking questions here. So let me let me finish Jefferson's question. So Jefferson was asking, do we clip or do we compress? And the answer there, Jefferson, is basically we compress the tone scale. So where on a standard RDT for a P3 digital cinema projector, the OSIS tones, the OSIS scale, and forgive me, I don't remember these numbers exactly, but OSIS 1.0 would be close to 48 nits, the maximum value of the cinema white. But there will be some compression that takes place in the RDT, and I'll do a little homework and try to recall what that is, but I'm guessing that 48 nits at the output of the RDT is probably OSIS maybe 2.0. I'll go and check that. And at that point, it clips. So there's some compression in the RDT, the output transform, but then there's also some clipping. The Dolby display, though, can basically keep going to a really high luminance, and I don't know what that luminance would be. There is a point eventually, and I think it's at OSIS 8 or so, where even the Dolby RRT will clip. And I don't know what that luminance level would be. Um, but I'll try to do some homework and find out. Um, so to Jefferson's question, there is compression and there may be clipping, but you'll want to master your movie in the ACES pipeline so that I'm guessing you'd want to master so you're never really above about 2.0 in the mastering. And how you master improved content that's useful to exercise the entire range of the Dolby display, well, you run the risk that then that content is going to clip on a theater projector. So there's not today any economic motivation to do that. Okay, so that's, I hope, addressing Jefferson's question. And then there's Siddharth is asking another question. Let me quickly read this. Dolby says, I guess, that they're ready for ACES. What do they mean? Do they have specific RRTs and ODTs built in for different display devices? Well, they're ready, I think, and really you should ask Dolby this question, but I think if I can give you my interpretation, I think this ACE is ready because they will operate correctly with an ACES RRT to mimic cinema display. They will also give you a Dolby ODT that makes the best of the Dolby display, which is to say really high contrast ratio. But choosing that ODT from Dolby, in my view, would compromise your display of cinema material. If you use all of that really, really high luminance information to really make specular highlights pop, or to make explosions, or to make lightsabers, you run the risk that that material will clip in cinema exhibition. So I think it's a little bit dangerous. But this is still evolving. We're not finished yet. ACES 1.0 has not yet shipped. We all, I think, appreciate the importance at the front end of ACES. All of this business at the front end of ACES is dramatically changing the way that people capture. So finally, we can do scene linear capture and transforms, make the cameras look the same even though they're from different manufacturers. All of those things are fairly mature in ACES. How we're going to deal with all this output stuff, honestly, there's still some open questions. Okay, now forgive me. I forget from last session, Mr. Tahari, your first name, but you've asked a question about ICC calibration of displays, and so let me spend a few minutes discussing that. So there are some display calibrators that are building ICC profiles. So let me take a quick snapshot of my notes here again and erase this and address that question about display calibration. So honestly, this is really it's very complicated. But let me see if I can make a summary and see if we can clarify. So let's start with the display, and I'll just give it an on-off switch instead of giving it knobs, because well, I know they have knobs, but that's an unfortunate feature of studio class displays. So internal to the display, there's some signal processing. And then those signals are applied to the display surface. In the broadcast studio arena, we're used to applying calibration internal to the display. We're used to a situation where when you present signals to the display, and here I'm drawing 3 lines because I want to present RGB to the display. Let's say when we present 709 to the display, it just shows up correctly on the display surface, and it's right. And if we want to calibrate that display, we use a measurement instrument to look at patches on the display. Sometimes the display has got a port for that instrument, and it just calibrates itself from the optical measurements of the probe. So that's one way to calibrate a display. In this case, the data that's presented to the display is the reference data. Now, this is often not the way it works for desktop computer graphics. So in desktop computer graphics, the more common scenario is we connect this display to a computer. We typically connect it to a graphics card, and that graphics card has got some hardware lookup tables on the output side. And the way we do monitor calibration is we don't connect the calibrator to the monitor itself. Instead, we connect the calibrator to a USB port, which is connected to some computer software, which loads that table. So the software systems load up the frame buffer on the graphics card with reference class calibrated data, but a transform is applied on the way out, and that transform is determined by the calibration system. So let me instead draw the calibration system down here. I'm going to try to correct my drawing by erasing this business. So we've got your application data going into the frame buffer. The calibration system has meanwhile loaded up the appropriate values into the lookup table. So often that process takes place by adapting an ICC profile and loading it into the lookup table. Now, this approach lets you do real-time business. So you can use the GPU to do high-speed playback or to do shading on the fly, that sort of thing. Now, one aspect of that way of doing calibration is that the only processing at the back end of a graphics card today is basically 3 1D LUTs. So you can load LUTs like that into the back end of the graphics card, but that 3 1D LUT provision does not allow you to either introduce or remove any interaction between or among the 3 channels. So think about film for a moment. If you're trying to emulate film, well, it's one of the characteristics of film that there's crosstalk among the dies that cannot be computed linearly. There's nonlinear crosstalk among the channels, and 3 1D LUTs cannot handle that. Now, you can, of course, simulate the crosstalk of film in a 3D LUT, but that cannot be executed real-time at the back end of a GPU. Now, you can use a GPU to introduce a 3D LUT. But when you do that, you now require the GPU to be running code dedicated to imposing that 3D LUT. Now, this is the case for high-end VFX and CGI systems that allow you to calibrate or display the look of film. But they basically take over the GPU. So you're no longer able to use any application. You must use an application, a software package that is driving the GPU. And so one example of that would be the TrueLight viewer, or even TrueLight itself. So you are running TrueLight, it has taken over the GPU. And forgive me, I can't remember off the top of my head the name of the Cinespace app. But there's a Cinespace app that allows you to impose 3D lookup tables like that as well. There's another Cinespace app, and I think they call it Equalize, or maybe there's no hyphen. But that app just inserts the 3-1D LUTs. So it does not allow you to either introduce or remove the film look. So in the case that you want a 3D LUT, you have to load that into an app that executes the 3D LUT, and those apps basically take over the GPU. So in that case, you build the film characteristic into the 3D LUT. Now, honestly, I don't think the film emulation is that important going forward, because going forward, all of us want to be doing the VFX and CGI math in an additive RGB space. So in other words, we want to have a working space which is additive RGB. And film, which I've demonstrated up here as CMY, is not additive. You know, you can call it non-additive, or you can call it nonlinear, although that's not a really useful term anymore. But the key point is it's non-additive. And, you know, I think I mentioned a few classes ago, the other example of a non-additive space is P7V2. So P7V2 is really one of the predecessors of P3 RGB. P7V2 was used in a couple of digital cinema releases in the early days. I'm talking about 10 years ago. The example that I can think of is Toy Story 2, where the digital cinema distribution master was in P7V3 space. And for that reason, you'll see digital cinema projectors and even a few direct view high-end mastering displays that have got this P7V2 setting available in the user interface. But please don't use that unless you absolutely know for certain that your material was created for that P7V2 space. The typical scenario today, of course, is we want P3 space. So that's a little bit about how calibration works and how ICC profiles relate to calibration. Now let me just check the chat thread and see if I've answered your questions. So Nick, you're asking basically, if I understand correctly, does AZO bypass loading the calibration LUT internally on the monitor? Well, AZO and even HP Dreamcolor are set up so that they basically, that they want to handle calibration this way. So you want to calibrate those displays internally to the display signal processing so that the RGB that you present to those displays has not been modified for that particular display. I mean, the disadvantage of this whole, build an ICC profile to calibrate my display, the disadvantage of that is when you build that ICC profile, you have effectively married that ICC profile to that display. Can I draw a wedding ring here to symbolize marriage? A shiny diamond ring. And that's not what EIZO wants to do. EIZO wants to allow you to use that display for any computer configuration, for any computer, for any software package, for any software load. So the advantage of using a high-end display like EIZO at the back end is you do not have to mess around with any either 3D 1D LUTs or any 3D LUT at the back end of the graphics system. You produce image data which is directly in your working space, and the EIZO will display that. So calibration is done within the signal processing of the display instead of being done within the GPU of the system that's driving that display. So I hope that answers that question. So now, I think all of that today was a really productive, I hope, productive discussion of the gamut issues and the calibration issues. Obviously, that's just improv, spontaneous class the whole way through. We're not going to get to our constant luminance topic, but we will do so next week. And we'll also next week get to some grading topics that relate to setting the knobs. But keep in mind, when you talk about grading, we shouldn't really be talking about setting any of the knobs on the picture you're looking at the moment. This entire discussion we had about profiling and calibrating, that's just the science of nailing the colors colorimetrically. That's not anything to do with the craft or the art of making the colors of the particular picture. Okay. Now we've still got this open issue of QuickTime gamma and gamma shift, and where to work in gamma spaces and where not to. So let me maybe do a 5-minute rant on that, and I'm absolutely open to any further questions that you have. I'm just quickly reviewing the chat channel, and I think I've addressed all of your questions today, but feel free to chime in with any further questions you may want to address today, and we'll see what we can do. But let me improvise on gamma a little bit, because this is an issue that several of you have commented on in the forums. Okay, so I think if it's Ali, if I'm remembering correctly, your gamma question was really focused on QuickTime gamma. But perhaps we can talk about the, thanks. Ali has just given me a link to the question in the forum. So let me very quickly go back and check that. Okay, so Ali, you're asking, does the gamma issue still exist in QuickTime? And the answer to that question is that gamma issue, the classic historical gamma issue, should now be gone. So at 10.6, Apple standardized sRGB class gamma, replacing the old historical QuickTime gamma 1.8. So gamma became 2.2. So going forward, the whole Macintosh infrastructure is assuming sRGB numbers whenever the images are in 8 bits or whenever the images are coded in nonlinear forms suitable for direct display. However, if you've got any legacy assets, they may have still been encoded with the old-fashioned gamma encoding. And if you've got any legacy software in your production pipeline, then you may have legacy software that's doing the wrong things. Now, as far as I can tell, all of the Final Cut Pro 10 infrastructure and the Apple Color infrastructure has all been, well, I mean, I should say, what's the remnants of Apple Color that are built into Final Cut Pro 10, they've all been updated to use the modern interpretation. But legacy assets may have 1.8 buried, and legacy applications may have 1.8 buried. So on those things, you just have to be cautious. So I guess my answer is, in general, the issue is gone. Everything is sRGB-ish by default. But you may ingest material that has got old QuickTime tags, and then you might be in trouble. Okay, so then I guess your next question is really, let's talk about the gamma shift problem. So I say that historically, a Macintosh system loaded a 1/1.5 lookup table. So let me just use a few minutes to say what I mean there. So basically, in the historical computer graphics situation, we had a frame buffer that in the old days was only 8 bits. So we had to put into that frame buffer information that came from the scene and got gamma corrected as if it were more or less coming from a camera. So we had scene linear tristimulus, call it T, and we applied a function something like a 0.45 or a 0.5 function to take 18% gray and put it halfway up the scale to be visually halfway. It was left to the display to invert that by using something like a 2.2. Now, the old Macintosh situation was that Mac had a frame buffer as well, but for reasons that aren't really perfectly well understood, Apple, instead of just doing nothing in that lookup table and being compatible with the rest of the industry, Apple instead loaded a very subtle curve into that lookup table. It was 1/1.45. So that's the historical output hardware path from an Apple frame buffer, and these would, of course, be QuickTime RGB values, out to the display, which did exactly what everyone else's display did 2.2. You know, Apple never made displays that were wacky. It was just this LUT that was a little strange. So the combination of those two was equivalent to a 1.8 power function instead of a 2.2. So when people say 1.8 Apple Gamma, they kind of think, oh, it's Apple displays that did a 1.8 instead of a 2.2. But in fact, Apple displays were identical to everybody else's displays. In the early days, they were just Sony displays badged Apple. Later on, Apple started contracting manufacture of their own displays. But it was never that the displays were 1.8. It was always that Apple was using a strange lookup table. Now, as far as everyone else in the industry was concerned, like, for example, the whole PC industry, They had lookup tables in the hardware at the back end too, but their lookup tables had a ramp, in other words, 1.0. The standard Microsoft-ish way to do this is just a ramp. Now, as we proceeded into the modern age, let me say the gamma shift problem is basically that if you've got image data, let's say originating on a PC, and you've got image data originating on a Mac, that image data is, the same image data, like code 128 on a PC goes out through this chain, code 128 on a Mac goes out through this chain. They produce different values of color. And the gamma shift problem is my image data was intended for a PC, but somebody accidentally sent it out to a Mac, or my image data originates in a Mac and somebody accidentally sent it out through a PC. That's the gamma shift problem. So basically, you repair the gamma shift problem either by applying or removing a 1 over 1.45 power function. Now, in the modern age, we've got frame buffers which have got way more than 8 bits. So, we may have effectively a 16-bit frame buffer, might even be floating point. And now we don't have to do this curve coming in at the front end. We can represent scene linear tristimulus values directly in, this is of course the GPU. And on the output lookup table, we can impose the function that's necessary to drive the display. So we impose the same sort of function that we would have imposed at the front end in an 8-bit system. Now we impose at the back end. So we still come out with data intended to drive a display directly. So we still anticipate something like a 2.2 at the display, but the lookup table is now going from scene linear tristimulus to the R prime, G prime, B prime values that are passed to the display. And this curve will typically be a 0.5 power function, or maybe, maybe you could call that a 1 over 2.2. That's close enough. Now, Margaret, I see that you're asking about 709 and its standard value of gamma 2.2. I'm sorry, of 2.4, whereas sRGB is 2.2. So basically, all of these numbers that I've shown you on the display side, I've been showing you sRGB numbers. And basically, though the 2.2 power is suitable when you're going out into a rather bright display, let's say 320 candelas per meter squared, and a rather bright ambient environment like the lights are on. You're not in a grading suite, you're not in a cinema. So the 2.2 number is suitable for those purposes. So let's put 320 nits, and let's say that what surrounds the image is something like 20% of the luminance value of diffuse or paper white. So this would be typical of a pretty bright environment, let's say an office environment. But when we master for HD, we master at 100 nits. And the ambient environment in the mastering suite has got a lightness, or luminance, I should say, value surrounding the mastering display that's only 1%. In fact, it's only 1% of one nit. In other words, the surround is only about one nit, as opposed to 20% of 320, which is 64 nits. So basically, there's 64 times less surrounding light in HD mastering than there is in a light environment. And in cinema, you might want to say, well, cinema white is 48 nits, but diffuse white, paper white, white shirt white is typically only portrayed on the screen at half of the maximum capability of the projector. And the surround there is 0%. So because there's different viewing conditions, it raises the question, can we take the same image material and portray it in all of those viewing conditions and get the appearance to match reasonably well? And the answer to that question, probably quite surprisingly, turns out to be yes, we can. And the way we do it is we mess around with the gamma number at the back end as a function of the display and viewing characteristics. And what we do basically is we choose gamma 2.2 in the bright situation, 2.4 in the dim HD situation, and 2.6 in the totally dark cinema situation. So the gamma numbers we use at display are a function of, let's call this the display characteristics, namely the luminance of white shirt white, and also the viewing conditions. Or you could call this the ambient or the display environment. So, Margaret, I think that's the answer to your question, that we can pretend in the creation community here that we're working in the HD scenario, but if we want to display that material in a really bright kind of office-like environment, we just display that material through 2.2 gamma at 320 nits. And roughly speaking, we can say that take the same material, put it in the cinema, just dial up gamma of 2.6, which is standard digital cinema gamma. Okay, so Ali is, and so I hope, Margaret, that answers your question. I see that Ali is following up on the gamma shift problem. So the gamma shift problem is not inside QuickTime 7 or inside Final Cut Pro 7. So we can install those things on 10.8.2 and have no problem. Oh, I'm not sure. I think that would be tricky. I don't know. I just have to say, Ali, I don't know the answer to that question, because there may be system level things within 10.8 that that cause gamma shift, even if you're running QuickTime 7 and Final Cut Pro 7. I don't know. It's a good question, but I have to take it as an open question. I'm not sure. Finally, I see that, and maybe we could have some discussion in the forums about that if anyone happens to know. It's a very exactly phrased question. There should be a yes or no answer, but I'm not sure what it is. So as a final point then, Peter is asking, isn't the output power function a historical leftover from CRT days? Do modern displays still have a physical power function, or is it just simulated for compatibility reasons? So that's an excellent question. And I guess I'll just answer quickly by voice without drawing anything. Basically, none of the modern display technologies have got a power function that mimics a CRT. I mean, a CRT intrinsically produces a power function something between 2.2 and 2.5. And that power in that function is more or less fixed and by the construction of the CRT itself. And what you measure really depends upon the black level that you dial in, either as a calibration control in the signal processing or the black level in the knob that's available or the setting that's available that's made available to the user. So as you bring the so-called quotes brightness, or what I would prefer to call black level, on the display setting up, you are effectively dropping the value of that exponent. So as you increase the so-called brightness setting, you are basically decreasing gamma down towards 2.2 or even towards 2.0. So that physical function is built into a CRT, but a DLP, PDP, OLED, LCD, they're all different. Those new displays do have compatibility circuitry to make them behave as if they're the old displays. But it's really valuable for us to maintain that old display mapping from code level to light level, because it's hugely important for compatibility reasons. But also there's a more subtle reason. It's not just compatibility. It's that the old gamma encoding turns out to be almost perfect perceptually. It almost perfectly matches the requirements of human perception. In other words, it matches CIE L-Star, or CIE Lab, as you might call it in Photoshop. And the new displays have got physical characteristics that do not have a good match to L-Star. Like DLPs and plasma displays have got an intrinsically linear characteristic, but that's not a good match to perception. And LCDs have got kind of a wacky S-curve that is also not a good match to perception. So those are all the reasons that we choose to maintain an RGB interface. And I'll go back and sketch on top of my graph again. You know, that this link here between the frame buffer and the display, even in the modern era of deep frame buffers, this is still widely an 8-bit display interface. I mean, even though we've got HDMI and high color and 12-bit and 16-bit and so on, this is still predominantly 8 bits in the real world. And it's only this power function behavior that lets us use that 8-bit channel, and that's a big deal. Okay, Peter, I hope that addresses your question about historical leftovers and native characteristic of displays. We're running over. Sorry, this is the longest we've gone. I'm running 12 minutes over. So we should wrap class 7 at that point. We come back to class, if I've got my numbers correct. So 1700 Eastern Standard Time, 2 days from now on Thursday. We'll see you all then. Thanks a lot.